Thank you very much, Fritz. Thank you all for coming. I'm very excited. My name is Andrew Lamb. I'm the staff engineer at Flux Data, and I'm also the Apache Arrow PMC chair. I'm on the Apache Arrow PMC, but I'm the Apache DataFusion PMC chair as well. So I'm going to talk to you first today about the technology behind DataFusion, a little bit like what it is, because I sort of assume a bunch of people in this room don't know. And then I'll talk about sort of what I think makes it a special project from the people perspective and how it's organized. So what is Apache DataFusion? At a high level, it's a top-level Apache project, right? This is about the governance, which I'll talk about it later. It's very permissively licensed. Here's the website. And just a spoiler, I'm going to basically spend this whole talk trying to convince you to both use it and contribute and help me make it better. So see how many times you can watch me try to fish for help. So what is DataFusion? The best thing I like to do, I think this is probably a technical audience, but I'll use my favorite analogy, but this is pretty low level, I'll admit. So many of the modern programming languages you know are underlied by something called LLVM, which stands, I think, for low level virtual machine or something. But I think that's, instead of each individual new programming language goes off and implements code generator and optimizer passes and the debugger support and all that sort of stuff. Instead, they all basically share the same foundation, which is LLVM, and the different languages like Swift or Clang or Julia or Rust, right? They all basically then focus on what makes their language different. So I think, well, that's kind of cool, whatever, it's a cost-saving measure. The coolest part about this is I think the real reason we've seen like an explosion in programming language innovation in the last 5-10 years is because to build a whole new programming language, you don't have to build it from the ground up anymore, right? You can basically start with LLVM, which takes care of all the low-level details, and you can then focus on what makes your programming language and environment unique, right? So obviously the analogy, DataFusion in my mind, is basically the same thing for analytic databases, right? So analytics. So instead of, at this point, we basically know how to build fast vectorized engines that operate on columnar file formats like Parquet. I know I was just at a conference, right? They've been talking about it for 20 years. Now when you're building the next generation data systems, and I have a bunch of examples to try to illustrate this, instead of focusing on the low-level details of making a fast engine or a SQL parser or SQL planner or something, instead you can basically spend the time on the application, what makes your application special, instead of reinventing the low-level pieces, right? So in my mind, this basically enables a whole new class of applications that you wouldn't have been able to build before, not because we don't know how to build it, but it's because it basically would be too infeasible to spend the time building, right? So I don't know, again, how many of you are database internals people at this is like the lowest level side, but I figured I had to at least throw it here. If you've ever seen anything about databases or how they're implemented, they would basically look like this. This is the DataFusion architecture, but they all basically look like this, at least in some level. You have data sources, some way to represent what data is there, how to find, where the files are. That's the catalog and data sources. There's a variety of front ends, right? That's the fancy way of saying like the SQL parser and planner. We also have a data frame API. There's a representation of how you calculate these results. You don't have to remember this. It's not going to be a quiz, by the way. Then there's a lower level physical representation, and then there's like the actual implementations of all these algorithms. The thing about DataFusion is you basically get all the green pieces, but you can basically change anything you want, right? So it's not designed to be like an end-to-end data system like Spark or DuckDB or something, right? Where the interface is SQL with files. This thing's designed to be a library that you build additional applications on top of. And the fact that you can extend basically everything is the key difference, all right? So don't just take my word for it. It's not just some other random project. We wrote a paper that got accepted to Sigma that I presented this past year, which is one of the big database conferences. I mostly point this, again, right, I'm trying to pitch you like you should use this thing. It's legitimate. We had it in a peer-reviewed paper, among other things. But I think it's real and now recognized across the industry as like a real piece of software, and that you can actually build products on top of. We also had top-of-the-line performance. This is our recent announcement that we're the fastest on the ClickBench benchmark. Now, I know there's all sorts of caveats about benchmarks or whatever, but the point is, this is basically like, you can get the same level of performance out of custom engines like DuckDB or ClickHouse, again, on the Parquet file format using DataFusion. So, by the way, speaking of fleeting, I actually looked yesterday. Some people clearly were gunning after us. We're no longer the top. However, we will be after we run the things on the next version. Which, by the way, we're looking for help if someone would like to help us run these benchmarks on the next version. I expect, whether or not we're exactly the top, whatever, I expect us to be up there in the running. So that's basically the point. The other thing is, if you follow Andy Pavlo, who's a big database professor at CMU, that might or might not mean anything to you, but if you're in the database world, it's definitely exciting. He runs a graduate level seminar class every fall. This fall he ran one about the new trend of databases, sort of building them out of database blocks. I was lucky enough to speak at the first talk, but then basically every other one except two were all built on top of DataFusion, which I think shows sort of how it's accelerating. All right, so I've kind of said this before, but the idea with DataFusion is I think it's 3 lines of command if you want to get a Rust program up and running, right? It's written in Rust, that can basically run SQL. It's like the equivalent of having DuckDB as a library. But then you can, as I said, very easily customize everything, right? Customize the file formats that you want, like your own custom file format I'm talking about, basically everything. So again, if you just want like SQL on files, be hard-pressed to say like DuckDB is maybe not a good choice for you, but if you want to actually get down and start customizing and have much more control over the engine, that's where you use DataFusion for. And it's designed basically let you start with a full-featured engine up front, and then you can sit there and customize whatever pieces are actually important for your use case. Yeah, makes sense? All right. So that's, and again, like in some ways it's an economic argument where instead of spending your engineering time rebuilding stuff that other people know how to do, right, you basically take the stuff that's standard out of the box and you spend your time focused on the pieces that are actually differentiating for your particular product. So now I'm just going to go through a bunch of examples of what people actually did with this thing, right, just as examples. So one thing you can do with them is you can build custom file formats. Like I talked about, there's a bunch of people talking about different custom file formats. The Lance file format is a new one that's designed for AI. You might ask, what's a query engine related to like a file format? Well, it turns out to make a fast columnar file format, you typically will do things like embed statistics in it or a variety of other things to make the query fast. And just the actual, or pushing predicates down into it is another thing you typically have to do. And so if you want to support that in your file format of your readers, you end up implementing a big chunk of what you would naturally see in a query engine anyway. So these guys use DataFusion to accelerate that, both to calculate statistics when they run it, but then also as the way to push predicates, like to filter out data while they're running. I don't know how many you want to make a new file format, but if you did, check it out, right? Another thing is probably you all have heard about if you're following the big data world is table formats, specifically Iceberg, Delta Lake, and Hootie, although I don't know if anyone hears about Hootie anymore, but Hootie's the third sort of major one. So to speak, but in fact, it turns out all those have aspects of query engines as well, and so all the Rust implementations of those file formats, not the Java ones, but the Rust ones, all use DataFusion under the covers because the table formats, yes, they store these are things that basically let you look at collections of Parquet files on Object Store and S3 or something as tables, but they all have extra levels of features like being able to write deltas or applying predicates, right? You want to delete certain rows, you got to express what rows you want to delete. That's basically ends up being a query engine. So if you're not careful, you end up re-implementing this stuff. And these people figured out not to do that with DataFusion. All right, another thing that's kind of interesting is people use this for SQL analysis, right? This was not something I would have thought of when I started using DataFusion, but there's a company called SDF gave these slides. What they do is people have these big ETL pipelines that are expressed as a set of SQL commands that by the time you get a report out the other end, you don't really know, you guys probably know this better than I, right? Like, where did that data come from? Was there any personally identifiable information there? Was it subject to certain data restrictions? And so they were basically using, what they do is they use the DataFusion internal structures to parse the queries into the logical plan representation, then did some sort of data flow analysis on it. Right? So you could basically track the provenance of data through to your own thing. And again, it's not like you couldn't have re-implemented that yourself, but the amount of effort required to build a plan representation that can represent sort of like the full range of craziness that's SQL is a substantial undertaking. By the way, this is also one of the cool things. They just got acquired by DBT I think last week, maybe 2 weeks ago, which now I'm very proud to tell. I tell all the VCs, I don't know if there's any VCs in here, that this is like the first startup that did a DataFusion powered product get acquired. So that often brings money to people's eyes. So anyway, I think it's that's a good story for DataFusion. And by the way, now we're in DBT, so I'm pretty excited to see what happens there. So that's using the front end, right? So all the DataFusion SQL parser and stuff. It turns out other people have just used the other pieces, which is the fast execution engine. So I don't know if you're familiar with Databricks' Photon engine or a project called Velox. Both of those aim to basically swap out native execution engines for Apache Spark because they can basically get 2 or 3 times faster using native code like C++ or Rust. There's another project called Apache Comet, started by a bunch of DataFusion Comet rather, started by a bunch of guys from Apple trying to do the same thing, right? Databricks Photon engine is not open source. Velox is run by Facebook. The Apple people didn't like either of those for some reason and are trying to build their own, but they're using DataFusion to do it, which is kind of cool. And of course, the thing that actually I think is the broadest use case, which we'll hear at least one other example of here tonight, is people building specialized database systems, right? If you want to build some specialized database system for a particular type of data, observability or time series are very popular with systems like greptime, InfluxDB, which is what I work on, InfluxDB 3 specifically, HoRADB, CoreLogic. There's a whole bunch of people using it for observability. But we've also had people build specialized engines for things like bioinformatics, which I never would have thought about, right? Like that's not Parquet at all. They have their own specialized formats, but apparently state-of-the-art data processing in bioinformatics, at least according to the talk from the guy who did Exxon, is a bunch of basically Linux executables that you string together as a shell script that like kind of you orchestrate your data flow that way. So he built some kind of more modern data orchestration tool based on DataFusion, which was pretty cool, like with his own table provider for the bioinformatics formats and stuff that did predicate push down in them. And then we have several examples of streaming, like I think Ozan will talk about that later, but there's a couple other systems that do like built streaming type SQL stuff. So I think that's the technical part. Hopefully that's interesting. And now I just want to spend a little more time. Again, this is all like a pitch of like why you could use this. This is okay, right? I'm not just a startup person, although I am like trying to sell you something necessarily. So I want to tell you about how the project is run and why it's a little bit different maybe than some other open source projects you've seen. This is basically just me saying I never have enough time, so please come help me. But let me go into the real meat of it. It's like who controls this, right? There's a lot of open source projects out there, probably too many. And there's always a real question of who actually controls the roadmap, who makes the decisions, and how does stuff get done. So DataFusion's not like there's not a startup, a DataFusion startup that's sort of pushing this. Instead, it's funded, aka the people who work on it are paid by companies that build products on top of DataFusion. So it's basically we're all working together on the shared foundation, right? So in some ways, just the economic, the simple version is the economics are just we're cutting costs by sharing development costs across across products. But I think there's a more interesting story too, because as the cost for this advanced analytic technology gets lower, right, that actually enables a whole bunch of people to build new applications that you wouldn't have been able to build before because you wouldn't have been able to afford it. So, basically there's no one yet paid to work on full time on DataFusion, including myself. I basically work I would say half time on DataFusion and half time on specific things for Influx. So obviously we're always a bit short on time. It's not like the most beautiful. I think we do a good job. But we could always use more time and more help. And on the upside though, I think it's kept us pretty good where we haven't been able to go invest in some crazy features, right, that just saddle us that no one uses because only the stuff that people are using is actually what people work on. So come on and join us. In terms of what that's actually generated, if you look at it, there's the Git history is a little tortured. So while the Git history will tell you there's like 700 distinct committers, I think the real number is more like 500. But that's still like a significant number of distinct individuals who contributed to this project over the course of, I think there's 8 years or so. The other thing is it wasn't started by Influx. It wasn't started by me. It wasn't started by, it was actually started by a guy named Andy Grove as like a side project. I think he really wanted to replace Spark. And along the way, he had to do a query engine. So he started DataFusion. And and he donated to the Apache Software Foundation, and then that's been able to contribute. There's currently 42 people who can write to the repository, right, or write access. Those are called committers, and there's 15 people on like 14 or 15. I can't remember if someone else has been added since that are on like the council that's charged with governing it, which realistically means deciding who else we should add to the writers. But basically, it's basically all community driven. I did the numbers. It's terrifying. There's like 96 distinct contributors in the 43 release. We release every month. We have done for the last 3 years, and there's 94 this past one. So it's like that's the velocity is pretty high. Now, of course, most of those people did one PR, but there's a significant number that did more. Yeah, it's been fun. So the final thing I want to talk about a little bit was the Apache Software Foundation, what that is. Again, I don't know how, maybe as a consultancy or Xomnia, you've seen this, right? Apache doesn't pay software developers. We don't pay people to work on software. Instead, this thing really acts as like a holding company for all the individual projects, and we can stick ourselves inside. We have some amount of like protection, but it really has basically solidified how you run an open source project in a sustainable manner. And what do I mean by that? Well, for one thing, right, if you go build your thing on top of DataFusion, you don't really have license risk. Whereas if you go pick some other random open source project, right, there's a non-trivial risk that, startups, the VC funding cycles might change, or they might swap your licenses, right? Like there's a bunch of examples recently of open source projects that the license switched, right? And now if you built some product or thing on top of it, you're kind of screwed, or at least you got to scramble, like fork the whole project. And OpenTofu, the Apache software license basically lets you do whatever you want except claim that you wrote it. And it hasn't changed in 20 years, and I don't think it's going to change again. So that the license is very stable and predictable. Basically everything happens in the open, which means sometimes there's lots of stuff to wade through, but it's all there if you want to see it. It's been very effective at attracting multi-vendor contribution. I was at a meetup like last week or 2 weeks ago, and one of the other speakers was from this company called Datadog, which why that's important is basically a competitor in some views to Influx, but yet the fact that this is an Apache Software Foundation project means that we can all like get together, work together, and still like move things forward, even though the companies themselves might not necessarily be the most friendly. Yeah, and it also shifts, like if someone life changes, right? It happens. Some of those people who have write access, I haven't seen them for 3 years. Some of them are super active. Sometimes they disappear for a year and they come back. Like you don't know, but the fact that this organization exists, it's been very good at keeping continuity. So anyway, my personal project goal is to get 1,000 projects working on DataFusion. I basically made this number up 4 years ago, mostly because it seemed like a suitably ambitious number, but like it wasn't outright ridiculous. But I think we're actually pretty close. Now, of course, I don't actually know because there's no requirement that you tell us if you're working on it. Please do, by the way, if you start working on it. But I think we're pretty close. Like this year, we'll probably have that. Now, of course, the vast majority of those like are things you've never heard of because they're hobbyist projects or whatever. But now at this scale, you can start seeing, right, there's startups that have built products on top of DataFusion. You're going to hear at least 2 more tonight, right? But also that have now gone through the cycle and got acquired. So I'm pretty psyched. So anyway, with that, I'm done. Thank you very much for listening. I don't know if I'm happy to take questions. Please go. It's all online. Many of these people actually I only know through GitHub. Like it's been wonderful to actually meet some of them in person. But basically everywhere. It's all open contribution. We'd love to have you. So thank you.
Yes, we are actually gonna do a short live demo. Pray to the demo gods so that we don't fuck up. All right. So this talk is gonna be a summary of the talk I gave in Carnegie Mellon's database building blocks seminar. I'm gonna skip some of the nerdy technical details. If there's anybody who wants to discuss the lower level details, I will be here after the talk and we will be able to go through them as well. The title of the talk is Towards Unified Compute Engines. So you can probably guess what I'm gonna allude to: Spark, Databricks, this kind of stuff. So let's get started. All right, so who are we? Let's first get that out of the way. I am one of the co-founders of our company, Sinara. My co-founder, Sami, is sitting here and he's gonna help me with the demo stuff. I've been working in data and AI space for the last decade, and I've been doing a lot of different types of work, including like machine learning models and training and all kinds of AI stuff and model monitoring and execution engines for all the data work that comes before the AI work. So it's not very unnatural that the company I co-founded with Sami tries to create this unified compute engine that actually brings together the entire end-to-end experience of building an infrastructure for this kind of stuff, because data exists for a purpose, and that purpose is to get value out of it. And one of the most versatile ways of getting value out of it is creating models and AI on top of it, right? Okay, so that's what Sinara does. We want to create this unified compute engine that will be able to give you this end-to-end experience, like what Databricks is trying to do, but using all the learnings from the past decade, all the learnings relating to cloud native and deployments and being like AI native, and how do you get AI stuff into your compute, and how do you do streaming and batch. There's a lot of challenges with respect to building these kinds of infrastructures. So just like DataFusion is trying to give you a simplified experience and hide the details of the lower level stuff, that's what we want to do. So this is, I think, a good example of why we need to do this. This is from Matt Turk's Data and AI Landscape. If you look at the tooling in 2012, we had a lot of companies doing a lot of stuff. Okay, but if you actually fast forward 10 years, now we have a lot of companies doing a lot of stuff. So obviously we have this problem of tooling complexity. There are too many tools. We are trying to do a lot of things, yes, but we are trying to do it with too many tools. It makes the experience of maintaining these kinds of infrastructures very troublesome. So if you're a small company, you don't need this complexity. You're okay. You can use things like, oh, I have Firebase and I use BigQuery and this, and you have 4 or 5 tools. You're done. If you're a very large company like a FANG, right? Okay, I'm Google. I can employ whoever I want. I can create my own platforms. I have like 1,000 engineers working on this stuff. No problem. If you're in the middle, right, then you have a very big problem. Like, am I going to have like 25 different open source technologies in my infrastructure? Some parts for like AI and some parts for data and some other things for like monitoring and observability and blah, blah, blah. So it becomes very hard. So we want to solve this problem, again, by applying all the learnings from the last 10 years. Can we solve this tooling complexity by going at the lowest level and solving those problems there so that application builders like you guys don't have to think about those, right? That's our mission statement. Okay, so let's make this concrete. Like, what does that actually mean? So imagine we're like building this application for traffic forecasting. Maybe like I have some microservices serving users API requests, whatever. And then I want to monitor this infrastructure. If there's a lot of traffic coming in, maybe I want to do something about load balancing, spin up more servers, whatever, right? Like this is a typical software engineering exercise. So how do you build a data application like this? How do you build this traffic forecasting application? Well, you have this like real-time data stream, which is the traffic data that is coming in. And then you have to obviously deploy some sort of logic on top of that stream. You look at the past traffic and maybe you've observed some patterns in that past traffic and you want to make a prediction. And based on that prediction, that forecast, you're going to take some sort of an action. Then you have to think about all of these things that you see here, right? Like, what kind of real-time technology am I going to use? Is it going to be like Flink or something else? How about like the interface? Am I going to program my data application in a SQL dialect? Am I going to do like Java? What is my API? How am I going to inject this sort of prediction into this? Right? Like prediction means some sort of machine learning model. So where does that model come from? Where do you train it? On what data? How do you monitor this? Because you have a prediction model, and that prediction model will go stale at some point. So you will need to retrain and update from time to time. So how do you do that? When do you do that? When do you know you need to do that? And how big is that model going to be? Like, is it going to run on GPUs? Is it large? Is it small? And all of those questions, these are the things that we think about. You guys probably think about that. Maybe not all of them. There's a division of responsibility, obviously, in any company. But these are the things that, at least if you're looking at it from a higher level, you would need to keep in mind. That's why we have that complexity that I showed you in the previous slide. Every logo there basically deals with a part of this stuff. Okay, so does that mean this complexity is unavoidable? Do we really have to have 25 different tools? The answer, we claim, is no. You cannot do it with one tool, but you shouldn't need 25 different tools. So this is a reimagining of how it could be if we had the right technology. So if you look at this query, which is a standard SQL query, it has one custom UDF, which is the forecast UDF. It basically says, I'm sure you guys are proficient at SQL, but I'm still going to repeat. Take a look at the last 4 hours, right? And then on the basis of those 4 hours of traffic data, make a forecast into the next 7 minutes, right? And then keep doing that. So it doesn't say, it hides a lot of the complexity behind, like what kinds of complexity. The last 4 hours could be a lot of traffic data. What if that's too big, it doesn't fit into memory, or how do you deal with that? Okay, let's assume that somehow that's hidden from me, that's abstracted away. What happens if this query fails? Because this query is going to run continuously and it's going to keep generating forecasts. If it fails, anything that depends on that forecast, we'll need to do something about it. So how do you deal with fault scenarios? And then, okay, let's assume that we abstract that away as well. So we have this forecast thing, which looks like an aggregation function. It's like a sum or average or something, right? So apparently it has a LSTM model behind it. It says use a LSTM as the first argument of that function. Where does that model stay? Like, how does that model work? Where is the inference done, right? How does that inference result come back to the engine? And if whatever we give out of the box is not suitable for your purposes, how do you create your own such functions, right? Yeah, yet another complexity is, okay, this query is running, and the picture says running. Let's assume that the scenario where it's running continuously. I just said you need to update this model from time to time. When does that happen, right? Like, it has to be taken care of by your engine too. What about the hyperparameters? So we say that the LSTM forecasts into the next 7 minutes, but there's like a lot of, like, what is the learning rate you used to update the model? It doesn't say, right? So just like it doesn't say anything about the fault scenarios or what happens if the window is too big, you will need to handle all of those at the lowest level of the engine itself so that the user doesn't have to think. They just write the business logic like what we did in here. So that's what we're trying to do. It's a very big problem. We haven't fully solved it. If we had fully solved it, we would be we would be like a unicorn right now. But that's what we aim to do. So that's the reimagining of that app without all of that complexity. So what do you need to do actually to create this app? You need to have, as you probably have guessed, like this query needs to run without differentiating between the streaming workload, which is the real-time traffic data, and handle all of that windowing and what if the window data is too big stuff. So the first problem we attacked was the streaming versus batch problem. This is called the Kappa architecture. And the holy grail is to have this unified engine that just takes in standard SQL and it is able to process both kinds of data. So if you have like this petabyte petabyte is too large. If you have like a bunch of terabytes of data, but it's fixed data, your engine should still be able to take it and run your SQL. And if it is not like just sitting there as a static data, but it is coming through maybe a Kafka topic, it's streaming to you, you should be able to use the same SQL query without changing it. If your query can run theoretically on that streaming Kafka source, it should. So that's the litmus test is, you dump your data into PostgreSQL, and if any query that works in PostgreSQL, which is pretty good at running queries on static data, conforming to the ISO SQL standard, it should also work in a unified engine. That's our desideratum, like that's what is desired from a unified query engine. So this is a problem we focused on for quite a while. And I like this example that will probably solidify what I mean. If you look at this query, what it basically says is, I have a stream of exchange rates. Let's say I want to dollarize all of my transactions. Maybe I have a transaction stream of all the sales coming in from different locations: Amsterdam, Istanbul, Austin, Texas, Boston, Massachusetts. Some of them are in dollars, some of them are in euros, some of them are in Turkish liras. So, and I want to track what's going on with my sales. So I have this stream of exchange rates and I have this stream of sales. And I want to deploy this so that I generate the dollarized sales continuously. This is a query that semantically does the job. For every transaction, you will look at the exchange rates that belong to the past. You cannot use a future exchange rate to dollarize a transaction. And you take the most recent one, right? But if you copy and paste this into Spark, it will not run. It will give you an error. But if you copy and paste this into PostgreSQL and run it on static data, remember which was our litmus test, it will work. I mean, it's a pretty simple query. So that's a good example of unification. Like, there is no reason why you should need to appease Spark to make this thing work and use their own syntax or whatever, right? So this is the problem that is a good example of the suite of problems we focused on at Sinara by using DataFusion. All right, so how can we do this? There's a lot of things you need to do. I'm not going to go into the full details of all of these things, but you need to have a very smart query planner, fully leverage any data ordering. Okay, your data has time series in it, and time always increases. It doesn't go back. Okay, you need to be able to use that. You need to have order preserving variants of all of the lower level operators that know how to exploit these kinds of monotonicity structures. And then you need your planner to be aware of, like, is this data coming from an unbounded stream? Is it coming from a fixed file and things like that? And then you need to have like mathematical techniques that are embedded to your execution engine that knows how to actually combine different calculations and still respect the monotonicity properties. So these are all like nerdy low-level stuff that you as the application builder shouldn't need to think about. But if your execution engine doesn't help you with that, then you need to actually think about these things. So these are some of the things that I go into detail in the Carnegie Mellon talk, and if you're interested, you can watch that as well. But we worked on these things, and we can, I think, skip the details and start the demo. So how does it work if you actually do all of that? And we obviously use DataFusion to implement all of those like things to abstract these away from you. This is basically how it works.
Okay,
so
I need to copy paste some.
All right. So the first thing he's gonna do is
increase the font size by a lot.
yes, we should. You are right. Yes. Is it a little bit more readable? More. Come on. Okay. Okay, so the first thing he does here is to basically create a table that has a bunch of transactions in a CSV file, right? And then, okay, so I have this table, and if I'm gonna look at like what's inside. Okay, this is what's inside. This is not new. You can do this with DuckDB as well. And then, okay, so I have this CSV file, and I'm gonna do some descriptive statistics. Okay, we can do that too with using Sinner and DataFusion. And where it becomes kind of interesting is, all right, so he's gonna do another query, but he's gonna create an app out of that query. And then he's gonna launch the UI, and this UI just created this app using that single ad hoc query. And then if you actually go into that app, you will see the query and you can run. But we don't have the time to build a app from scratch in this talk, so we're going to show you a ready-made app that we created. This app looks like looks like a Notion document, right? So it is similar to the traffic forecast scenario that I gave as the motivating example. What it basically does is to basically fetch costs from microservices that are running in some cloud instance, and it's going to look at the average cost over some period of time per microservice that exceeds a threshold. Let's say I have a budget, right? And if it actually exceeds that cost threshold, then it actually joins this event with logs and metrics so that I can debug why my microservice is so inefficient and costing me a lot of dollars. So this query is what expresses that logic. What's interesting here is if you go down, you will see some like left joins and stuff like that. So, okay, there is nothing very interesting about these. If you run it on Snowflake or if you run it on Postgres, they will happily run this. But again, if you actually try to do this in an online setting with streaming data, no engine will run this. Even though if you do a theoretical analysis on this query, it should be executable, right? So we built a fork of Apache DataFusion that is able to do this kind of analysis and then actually run the query if it is theoretically runnable. So here he's basically gonna do the demo for you. So we have these like sources. I said we are gonna look at the cost stream. We don't have that just yet. So he's gonna attach that cost stream. This is gonna actually talk to a Kafka cluster somewhere in the cloud. And that is now defined as a data set. You see this cost stream stuff. So he's going to start pushing some data into this Kafka cluster. Okay, so these are like simple blocks that push data into Kafka clusters we created for demo purposes. And then if he runs the query, let's pray to the demo gods that it runs. All right, it seems to run. So it's going to run continuously. And if you look at what's below, you will see this kind of label, which is very small, but it's a label. That label is actually denoting this stream that we are like building right now continuously. So the whole point is you will be able to create another query underneath to keep going. So basically build a compound data application. My first step is to do this, and then I join it with that, and I do this, and I do that. And then you can iterate locally with this Notion-like experience, right? And when you are done, if you are successful, you will be able to deploy to the cloud where it runs with horizontal scaling and fault tolerance and all the shenanigans. So just like DuckDB is giving you this experience of, hey, I want to prototype these ad hoc queries very fast locally to know what I'm doing and make all the mistakes locally in my laptop. We want to give you the experience of building a data app, an end-to-end data app within the comfort of your laptop, so that you make your mistakes in here, and then when you're ready, you spin up some workers. You don't make any change to your business logic. You just upstream it to the cloud, and you have it deployed and running. So that's all for the demo, right? I'm going to conclude by basically, we're going to skip all these there. They are in the CMU talk. You can check it out. I'm just going to give you a 2 minutes teaser on what's going to come next. So here in the demo, I gave like this rule kind of data app. Okay, if the cost exceeds this, blah, blah, blah. But my motivating example was using a model, right? So the whole point is you want to be able to build these data apps in an AI native way with AI models inside. So how do you do that? As I said, you will need to create these like functions that encapsulate these AI. So we built this library called Mithril, and the library basically is a library like Keras. I don't know if you guys use Keras for like building machine learning models. But it brings all of the best practices from the compilers world and the databases world into AI. And you don't need to concern yourself with, is it going to run on Torch or JAX or something else, or how do I optimize what happens with the gradients? None of that. You actually build a logical plan for your model, and then you compile it with a backend. This could be an Arrow backend, for example, to integrate it with a DataFusion-based engine. It could be JAX backend, it could be Torch, it could be TensorFlow, whatever you want to do with it. And you can specify, precisions. You can specify parallelization. I want to shard my data this way so that I can use multiple GPUs and stuff like that. And then after compile, you have this usable UDF, and you can happily build your data apps. So this is open source. It's also Apache license. We recently open sourced this. When I gave the CMU talk like a month, 2 months ago, it wasn't open source yet, so it's very new. We haven't made the public release yet. We would love if you guys, checked it out and played with it and created issues and gave us feedback, so we can deliver high quality software for all the practitioners like you. And we would be very happy if you can start it and support it as well if you like it. I guess that's all for the talk. Thanks for listening.
Thank you so much for having me, and also thanks for organizing this event. I'm excited to talk to you about incremental data pipelines with DataFusion and Iceberg materialized views today. But before I jump into how we can use materialized views with DataFusion, I want to motivate why materialized views are great for the user experience. And for that, I'd like to have a look at how analytical data processing works, and then as a first step, contrast this with transactional databases, and especially how data gets inserted into transactional systems. So if we look at transactional systems, we see that the data is always generated inside the process and then inserted into the system. There's never another record of the data anywhere else. It gets created and inserted into the database. You can see this when you're looking at, for example, when a user signs up on a website or creates an online order, he inserts the data and it gets inserted into the system. This is in contrast to analytical system, where the data typically already exists, and we're deriving our more data from this existing data. It never happens that you go to an analytical system and you just insert like a single tuple with data you just created. And the cool thing is that you can always, since this data already exists, you can also reference this data. And this leads to also like DBT tools like that, where you can use views for your data transformation. And with that, you first replicate the data from your source systems into your analytical systems. And since you can reference this data, you can then express any transformations you want to do as a view. I've depicted it here as a SQL query. I'm not sure like how proficient you are with SQL or if you're using data frame libraries, but you could imagine this also be using with data frame libraries. And so as a user perspective, views are pretty great because you don't have to worry about, have I processed this data already, or what happens if I'm rerunning the query, like am I duplicating any data? If you're using tables, you always have to worry about these kind of things. The only issue is that views can lead to redundant computation, because if you query a view, it will run the entire query every time you query it. And since most of your data actually doesn't change, you're rerunning a computation that has been running before, and you're just redoing the same things. And it's like in most cases, the amount of data that gets updated or inserted into the system is really small compared to the amount of data that's just lying in the system and hasn't changed in a while. So if you're using views, you would perform all this computation. That's where materialized views come into play. They combine the simplicity of views as a user with the performance of tables. Just like views, materialized views are defined as a query. But unlike views, they pre-compute this query beforehand, and when they are executed, they return the already computed results to the user without needing to rerun the query again. And another thing they enable is incremental refresh, which I will get back to in a second. And since there's such a nice combination between the simplicity of use and the performance of tables, we see more and more materialized view-like products being introduced in the industry. We have Delta Live tables from Databricks, we have reflections from Dremio, and dynamic tables from Snowflake, which all are kind of the same concept as materialized views. The only problems with these products are that they lock you into their vendor ecosystem. If you use Delta Live tables, you can only query them from Databricks. You cannot use another open source query engine like DuckDB or Polos or whatever to access the data because it's their proprietary format. And just like Iceberg tables are a vendor-neutral standard to store your data, I would like to see a future where Iceberg materialized views are an open standard to express your data transformations. And with an open standard for materialized views, you can define your data transformations, your business metrics once, and you can choose whatever query engine you would like to transform them or to access the data. And this also enables you to choose the best tool for the job. You could use one query engine for a big data pipeline where you have to process a lot of data, but you could use another the query engine, like a single node query engine like DataFusion, to execute a smaller pipeline. And you wouldn't need to pay always the cost of a big query engine. So that's the vision. And I've created a PR to the Apache Iceberg project, and we're in the process of integrating it into the process into the project. And I'm really hopeful that this will happen in the next couple of months. So this is the vision, and this is the motivation for materialized views. And since we're here at the DataFusion, since the topic of today is DataFusion, I also think that these materialized views are great opportunities for single node query engines, because if we incrementally process the data, we can reduce the amount of data we need to process, and therefore can also use smaller engines. So in the next part, I want to go a bit into incremental view maintenance, how we can keep these materialized views up to date. And there are different topics different techniques to do incremental view maintenance. And first I'm gonna quickly explain what it means. And so if we think of a view or a materialized view, it can be thought of as an operation which takes certain inputs and produces an output. In case of a materialized views, it will store this output. But typically, these inputs change over time because new data gets inserted into the system. And the point of incremental view maintenance is to avoid running the entire operation again in order to get the updated output. The goal is to calculate the new output by reusing the old output and also using the changes to the inputs. And the hypothesis is, since only a small part of our data changes daily or in certain intervals, you can save a lot of computational time. So as I said, there are multiple techniques to incremental view maintenance, and there also has been a talk on a previous DataFusion meetup presenting one, but I'm going into the topic of algebraic incremental view maintenance, where we try to calculate the next state of our output from the previous state and use certain functions which define how we can calculate the rows we need to add and the rows we need to delete from our previous state. So these are these two functions here, delta and nabla, and this framework introduced by Griffin and Lipkin gives us the formulas to calculate these functions. And now I want to go through a couple of relational algebra operators. I'm not sure how well you're versed with relational algebra operators, but I hope we get the gist of it. So if we think of a select clause in SQL, it's referred to as a projection, which just selects certain columns from an input. And here on the left side, we see the input R and the change to the input delta R. On the right, on the top right, we see how this projection operator works on the original input. So we just select the customer ID and quantity columns from the input on the left side. And on the bottom right, we have this formula for calculating which rows to add to this new state. And the formula says, okay, for a projection operator, it's actually also just applying the projection to the input. So we're also just taking the customer ID and quantity column from the delta. So it's pretty easy. You just apply the same operation to the delta and you're done. Very similar for the filter operation. Again, you have the inputs on the left side. We're filtering all rows which have a quantity larger than 10 and get the results on the right side. And again, on the bottom right, the formula for calculating the delta is that we just need to apply the same filter to the input change that we get. It gets a bit more interesting if we are looking at joins. This time we have two inputs and their corresponding changes on the left side, R and S. And if we look at the top right, we see the result of an inner join of the original states of our inputs. And when we now look at the formula on how to calculate the differences to our expression, we see that it's composed of three parts. The first part is joining the two delta tables at the bottom. And we see that there we have a matching row where the customer ID is 4. So on the right side, we get this part of the equation, we get the line with customer ID 4. Then we get a second part to the delta, which is joining the table delta R and the S table. which gives us the row matching the customer ID 2. And the last part is matching R with delta S, which is empty in this case. So this way we can calculate the rows we need to add for a join. Also complicated expressions for aggregations, but it's actually not so complicated if you think about it. Again, on the left hand side we have the inputs to the expressions. The symbols can be very daunting and unappealing, but in the end, on the top right, we're doing a summation over the quantity column and grouping by the customer ID. That's the result of the old state is on the top right. And if we want to update this with the aggregate operation, we now have a special case that we have to delete rows even when we didn't have any deletes in the input change, because we have to update the rows where the aggregate values changed from the last time. So the first contribution we see here on the right deletes the rows where the aggregate value changed from the last time. And we get that by joining the delta R table with our last result. And so we deleted the old value of our aggregate function, but now we have to kind of add the new value for this line. And there we're using a special kind of aggregation. And as a last part, we have to add the lines that haven't had an aggregate value before. But I don't want to bore you too much with this. These are just the equations, how you can calculate which rows you need to add or delete from the table. So now that we know kind of what theoretically we need to implement to be able to update our view according to the input changes, I want to show you my experience with implementing this with DataFusion. The general process looks like this. So I have the view SQL, which I will translate or parse into a DataFusion logical plan at the beginning. And then I can use the tree-node API from DataFusion to transform this logical plan according to the rules that I just presented to you into a new delta plan, which I can calculate to get the rows which I have to add or delete. And that's where the great API of DataFusion comes into play. You can customize almost everything, and you have all the tools at your disposal to do such things. We can then execute this delta plan and insert the calculated rows into a table, and thereby gets the updated results of our materialized view. One issue you run into when you want to implement this algebraic incremental view maintenance is that you get duplicate nodes in your logical plan. Like if you look at the formulas I presented to you for the join, for example, in the original statement you have like single entities of both expressions, but if in the transformed expression you always have duplicate nodes. And at the bottom here the logical plan is presented for that. And you can see that we have these duplicate nodes, which means also that the entire subtree that is below that also gets duplicated. And if you have a 3-way join, a 4-way join, can lead to you needing to scan the same table 8 or 16 times, which obviously isn't great for performance. So when you do that, you're losing probably performance compared to if you just run a full refresh. So what I implemented is this fork node extension where you're connecting two nodes with channels, and the first node of these two, which gets executed, executes its children, clones the results, sends them through the channel to the other node, and the other node doesn't execute its children and just takes the results through the channel and passes them on. And in this way, you can avoid duplicating all this computation in the graph. So I've brought a benchmark. I've ran this on the TPCH query 12 with TPCH data scale factor 10. You can see the query on the left-hand side. It includes one join and also an aggregate expression. I would have liked to show you more impressive results, like more savings here, but this is kind of still like early days for this project. And so currently I'm doing two passes where one pass gives me the rows which I want to add, and another pass gives me the rows which I want to delete. And both of these passes contain results which could be shared. So I'm actually duplicating the work. So I think there's a pretty obvious performance gain that you can get, like 2x performance, like very obvious. I didn't have the time to do it now. And there's probably even like more performance increases you can do there. So, but I think the general direction is there that with these incremental processing, you can save the amount of data you need to process, and then it makes it easier to switch from maybe like a large distributed query engine to a single node query engine, and you can save a lot of money in the end. That's it. Thank you for listening. And if you have any questions, yes.
You should go back to the last slide. Like, don't undersell yourself. That's replacing a quarter of the lineup. Like, that's replacing a huge amount of the data, right? So the fact you're doing half the time is still a major win.
Yeah.
That's not like updating 3 rows, right? That's updating 2 gigabytes out of a 10 gigabyte data set.
True, yeah. Yeah, I think like especially for like if writing is the bottleneck, then like with the full refresh, you often always have to refresh the entire table, and like even if you maybe spend some time computing, like only updating the small parts gives you also a big win. Yes.
I think I have ideas on how to make this at least 10x.
Yeah, I can imagine, yes.